When information falls into a black hole, physics says it cannot disappear. Plainly, information survives in some form, not erased forever. We can track where that information might hide. Imagine a particle's history written like a tiny barcode on it. In physics, information means the quantum state that specifies a system. This matters because losing that data would break fundamental laws. Quantum states evolve reversibly under unitary rules, preserving information over time. Noise or measurement appears to erase information, yet underlying correlations remain. A hydrogen atom's electron has about 200 billion possible energy microstates. A gram of hot gas can encode roughly 10 to the power of 23 configurations. So information means the full quantum pattern that defines a system. A black hole looks like a dark well in space, swallowing light. An event horizon is the point beyond which nothing returns to observers. This boundary decides whether information remains accessible to outside observers. Classically, anything crossing the horizon is causally disconnected from outside space. Quantum mechanically, fields near the horizon entangle with interior degrees of freedom. Our galaxy's central black hole contains about 4 million solar masses. Its horizon spans roughly 20 million kilometers across, enormous in scale. Thus, the horizon is both a physical barrier and an information interface. Near a black hole, the vacuum seethes with virtual particles popping constantly. Hawking radiation is thermal emission produced by quantum effects at the horizon. It slowly reduces mass, so where the information goes becomes critical. Pairs of particles form near the horizon, one escapes, one falls in. The escaping particle carries away energy, causing the black hole to shrink gradually. It is extremely cold, around 110 to the power of -8 Kelvin. Thus, evaporation takes far longer than the age of the universe for large holes. So Hawking radiation forces the information puzzle. It's not an easy escape. Picture a hologram where a flat image encodes a full three-dimensional world. The holographic principle claims volume information can live on a boundary surface. It matters because it offers a route to save information from loss. In some theories, bulk physics maps exactly to a boundary quantum theory without gravity. Degrees of freedom on the surface reproduce interior dynamics, preserving quantum correlations. Black hole entropy scales with area, about 10 to the power of 77. ADS/CFT provides a concrete example where the mapping works mathematically, so the surface might carry the book of the interior, line by line. Inside the horizon, information mixes like ink swirling in a stormy sea. Scrambling means information spreads into many microscopic degrees, becoming inaccessible locally. Fast scrambling protects quantum information, yet it complicates recovery efforts. Interactions amplify small differences, creating complex entanglement across the horizon. Black holes seem to be the fastest scramblers allowed by physics, by conjecture. For a solar mass black hole, scrambling completes in between 1 and 10 milliseconds. Soft hair are low-energy excitations on the horizon that may store information. Thus, horizons act like chaotic encoders, hiding patterns in subtle surface wiggles. Some proposals paint a violent place at the horizon, burning all that falls. A firewall is a hypothesized energetic wall replacing the smooth horizon. If true, firewalls would destroy infalling observers, breaking relativity's expectations. Other ideas include long-lived remnants that keep information trapped indefinitely. Some suggest baby universes siphon information away, creating separate causal domains. Remnants could sit at Planck mass scales, about 10 to the -5 grams. So alternatives range from destructive walls to tiny information storing relics. Telescopes and detectors give us real probes of extreme gravity nearby. Tests look for subtle signals that betray information leakage or echoes. Confirming any signal would change our understanding of quantum gravity. LIGO searches for gravitational wave echoes after black hole mergers, potentially revealing structure. Event Horizon Telescope images horizons directly, constraining surface models observationally. LIGO observes frequencies between 10 and 1000 Hz, catching mergers. So experiments are beginning to test smoke signals from the information problem. We began with the claim that information isn't simply erased by black holes. If you found this curious, subscribe for more deep dives into cosmic mysteries.